So this is E698G, lecture 22. So let's now start with a differential amplifier with a LC tank load, right? And in doing this, our approach is same as before. We'll first analyze the differential amplifier with the LC tank in open loop. Right? And especially we are going to look at its behavior if we feed in an input at the resonant frequency of the tank at omega naught. Right? Then we will put this in feedback. So we'll put one stage in feedback and check if it oscillates. Right? If it doesn't oscillate, then we'll put two stages in feedback and check whether it can oscillate. And then we'll repeat till we reach a point where it can oscillate. Okay? So how does a differential amplifier look like? So we'll have a tail current source. Let's say this has a current ISS. Typically, you would have the load here. And let me call these points as Vx and Vy. Let's say this is transistor M1, M2. This is some input V in P and V in M. Now we replace this load with an LC tank. I'm directly going to draw the parallel RLC here. Now so under steady state, let's say I applied some common mode voltage to both inputs, right? Then what is the current you expect to see in M1? So this is going to be ISS by 2, and the same current ISS by 2 is going to flow through M2 as well. Now let me apply some input V in between both these terminals. So this is one terminal and this is the other terminal. So I'm applying some V in between them, and we'll apply this in a differential sense, meaning that this will be plus V in by 2 and this terminal is going to be at minus V in by 2. Okay. Now in this case what happens? So you will have a steady state current of ISS by 2 flowing through this. If I have V in by 2 applied here, what happens to this current? Assume a GM for the transistor. So you'll have an incremental current of GM V in by 2 flowing like this, right? And that same current is going to flow up like this. Now if your GM is large enough, right, then you will be able to completely switch this ISS to one of the branches at a time. Right? Which means if your GM is large enough and you applied a positive, if the V in by 2 is a positive number and minus V in by 2 of course is a negative number, then you can have all of ISS flowing through this and zero current through this branch. You are completely switching the tail current source. Okay. Now let's assume, because we know that you can expect to see outputs only at omega naught, right? Because the tank is going to offer the maximum resistance at omega naught. Let's assume that I have fed in a V in, which is equal to some A naught into sine of, let's say, cos of omega naught t. Right? I'm simply going to sketch the currents Ix and Iy. Again, assuming that the GM of the transistors is large enough, how will Ix look like? Correct, but the current is completely, GM is very large and the current is getting switched completely to one of the branches. Right? So you can expect to see sort of a square wave for Ix, right? Goes from Is to 0. Right? Similarly, the Iy is going to simply be the opposite. Okay, and what is the average value of this? This is equal to ISS by 2. Okay,
what
so
did you do for switching you did?
Just that I have designed with a very large GM. So the moment you have a positive value here, the current completely switches to one side. Okay. Now for a minute, simply assume that your Ix and Iy are ideal square waves. Right. So it is going from ISS to 0 like this. Right. Now I can calculate its Fourier series, meaning I can calculate the frequency content in the Ix waveform. And so when I calculate it, if this was an ideal square wave, right, you would see some DC component, let's call it as I0, plus what all harmonics do you expect to see at the output? Only the odd harmonics, right? So you will see the fundamental at, let's say, I1 into cos of omega naught t, plus some I3 into cos of 3 omega naught t, plus etc. So far okay? Now the tank is very narrow band, right? The tank is going to offer a good impedance only around omega naught, which means even though all of these currents are going to flow through omega naught, flow through the tank, only this component is going to generate a significant potential across it. Is that okay? So you will have I1 cos omega naught t getting multiplied with Rp, generating a potential at the output. Is that okay? The current flowing into the tank is not a sinusoidal. It has a lot of harmonics. But only the component at omega naught is generating a potential across the tank. Sorry? The voltage output is a sinusoid. Right? So if I give something like this, Vx and Vy is going to be sinusoidal waveforms at omega naught. So far okay? Now we can also calculate what is the amplitude of the sinusoidal waveform at the output. Can you comment on what this I0 is? Right. I0 is the DC component or the average of the Ix waveform. So this is going to be ISS by 2. What is I1? What is the numbers that you remember? I mean, what are the possibilities?
4 by 5.
So it's either 4 by pi. Anybody thinks it should be 2 by pi? Any other numbers that you think of? There is no under root. I mean, the numbers I usually get confused are whether it is 4 by pi or 2 by pi. If you have a confusion, I can tell you a quick way to remember between the two. 4 by pi. So let me tell you how I remember between these two numbers. Right. So if you have a square wave, the Fourier series is trying to approximate the square wave as a summation of multiple sinusoids, right? So we know that the fundamental is going to be there, right? And fundamental amplitude is what we have a confusion, whether it is 4 by pi or whether it is 2 by pi, right? So let me consider the case of 4 by pi. Let's say the signal is going from -1 to +1. Okay. So if it's 4 by pi, is this going to be bigger than the square wave, or is it going to be smaller than the square wave? Bigger than the square wave, right? So you'll have a signal like this, right? All the other higher harmonics are going to be smaller than the square wave because the strength of the harmonics is reducing by 1 by n. right? So your next harmonic, which will be the 3 omega naught, is going to be somewhere like this, right? And we want all of these harmonics to add up and bring down this level as well as fill up these levels so that it becomes like a square wave, right? Now if you chose 2 by pi, this 2 by pi is going to be smaller. 2 by pi is going to be something like this, right? So no matter how many harmonics you add, you will not be able to match up to the square wave. So the fundamental has to be larger than the square wave itself. So now depending on whether you go from -1 to 1 or 0 to 1, you can take a call, whether it is 4 by pi or 2 by pi. Okay, so now in this particular case, you have the signal going from 0 to ISS. If you remove the DC component, then you will get minus ISS by 2 to plus ISS by 2.
4 by 5 should be the ISS.
So it is 4 by pi into ISS by 2. Is this okay? Any confusions on this? Right. So then I can write the strength of the signal at Vx and Vy. So at Vx, the peak value is going to be 4 by pi into ISS by 2 into Rp. This is okay? So that is simply 2 by pi into ISS into Rp. Now let us look at the peak value of the differential input. So I am interested in Vx minus Vy peak value. How much would this be? Twice of this, right? So 4 by pi into ISS into Rp. We can also look at what is the peak to peak value of the differential output, and that will be double of this. 8 by pi into ISS into Rp. What are we looking at? These are the output nodes. So now any signal you apply at Vin at omega naught, right, it is going to cause some current through the transistors M1 and M2, right, and that is going to be periodic at omega naught, which means it will have some fundamental at omega naught, possibly some DC value, as well as higher order harmonics. Always the fundamental is going to generate a voltage at the output. Okay? So you can look at what is the current profile you expect, and you can look at the fundamental of that and calculate the output signal. It will have, the frequency will be at omega naught and the amplitude will directly correlate with the amplitude of the fundamental. Okay? Right. So now we take the circuit and connect it in feedback to see if we can generate an oscillation. So we start by taking 1 unit first. So we have 2 inputs at these 2 nodes, and we have 2 points where we can take the output, right? Which means there are 2 ways in which we could put this in feedback, right? We could connect like this, or we could crisscross it and then connect it. So we will try both and see where we are getting lucky. So in the first case, let's say, sorry? Crisscrossing as in, that was, so crisscrossing as in we take, connect inputs directly like this. So let's say this was V and P and V and M. Do you think this can give us an oscillation? So what we have done is, you have an amplifier right? And we have simply connected the input like this. So now if you wanted to apply Barkhausen criteria, we can simply check, break the loop and check if I go around the loop, I am able to overall get a 360 degree. Right? So the question is, if I go around the loop, do I get 360 degree? So if I apply some V in here, what comes back? You get minus V in, right? So is it 360 degree? It's only 180 degree, right? Therefore this cannot oscillate. Now in the overall loop, you need positive feedback, 360 degree. So why you are having that doubt is, right? If I consider a loop like this has to give me 180 degree and the overall loop has to give me 360 degree. So now I connect it the other way. I take the input from M1 and connect it to Vy. I take it from Vx and I connect it here. Okay, so this is same as, let us put it in so now I crisscross the outputs like this and then connect it. So now can you tell me if this is in positive feedback or negative feedback or something in between? This is in positive feedback, right? If I give some plus V in here, right, I can break the loop and check here. So you get minus some gain times V in, let me call it as some A times V in, right? And this comes back again as a positive quantity here, right? So if I break the loop and then go around, you will see that this is able to give you a positive feedback. Oh, we didn't. So all that we did is there are two ways in which we could have connected it, right? I could have connected V in P to Vx, or I could have connected V in P to Vy. There are two possibilities, so we sketched out both. That's all. We are taking one differential amplifier with a LC tank load, and we are now trying to see if one stage can give you an oscillation. Right? Because there were two terminals for the input port and two terminals for the output port, there are two possibilities in which you can put those in feedback. So we have tried out both the possibilities. One of them is not going to give you oscillation. The second method is able to give you oscillation. Is that okay? So now let me make this a little pretty. I will sketch the transistors inwards. Where do I connect this? Gets connected here. This gets connected here. Does this remind you of something? Right, but we have already called something as a cross-coupled oscillator. So what should we do this? But how do you, what is the main difference between this architecture and the architecture you have seen before? Right, so now we have a tail current source. So we'll call this as a cross-coupled oscillator with a tail current source. Okay. So now, if you did you see any benefit between this cross-coupled oscillator with a tail current source and the one without the tail current source? Sorry, So the amplitude of oscillation at the output, right? You can control that using ISS. Right? In the other case, it was not well defined. If you make sure that your ISS is steady. Sorry?
You can just control the DC part, right?
No, I didn't follow. What do you mean by control the DC part?
How are you controlling that amplitude of the small signal to ISS?
So once you control the, okay, I understand your question. So the analysis that we have done, right now, does this assume small signal analysis? Does this assume a linear model? Nothing, right? So this is the most generic analysis that you can do. It doesn't assume a linear model. It doesn't assume small signal. So you can have large signal swings and then still get the amplitude.
But how is ISS controlling that amplitude?
Like just we derived right now. If you make sure that your GM is large, right? When you have switching waveforms at the gate, all of this ISS is going to either flow through one branch or the other. So you will have square wave-ish current forms through the transistors.
And then we don't apply VCM.
Where is VCM applied? Right? So that way you can still control. So the amplitude is going to be 4 by pi ISS-R. Any questions on this? You can take a minute to see if you have any doubts.
That reduces to RPM
At omega naught. Yeah.
what can be small signal?
Did we do small signal for that?
We did that. We did the small signal that Z up, Z down.
That is when we were looking. No, I didn't follow the question. Can you repeat it? Your question is whether the LC tank reducing down to RP at omega naught.
Linked to small signal.
Is that linked to small signal? So,
No.
what happens if the signal swings are large? Is there anything limiting it? Nothing is limiting it, right? So you can have an R, L, and C. And if some current is flowing through this at omega naught, then the voltage developed across that is In into Rp. The voltage levels of the current is not going to limit that assumption. Right? So small signal assumption is not made here. Okay. There was another question here. Okay. Alright. So now if so much is clear, let me also introduce you to the other way of looking at oscillators, which is the one port view of analyzing the oscillator. So let's say I take a resonator. If this is an ideal resonator, such as the LC tank, if I create an initial condition, then this is going to oscillate forever, right? If I initially dump some energy on it, that energy is going to simply slosh between the two elements, two reactive elements, and you will have oscillations forever, right? Now, if this is a lossy resonator, what happens? This is simply going to die off after some time, right? The rate at which it is going to die off will depend on how much losses are present in the resonator. Now, let's say I take another element that is able to replenish the losses in the resonator every cycle. For example, let's say I have a pendulum. If I start a pendulum from this position, it's going to swing. But because of friction, it's going to stop eventually. Now let's say every time it comes back to this position, I give it a small push, such that it is able to overcome the friction it faced in that cycle. Then I can get this system to swing forever. So the same method, every cycle some energy is lost from the resonator. I will connect another component here that is able to replenish that energy in every cycle. So if the lossy element was some resistance Rp, I have to connect minus Rp here. So of course, you don't get negative resistances directly. You will have to use active implementation to realize a negative resistance, right? And we saw examples of this in some of the problems that we solved, especially the last problem we solved where we had the inductor, capacitance, and some resistance, right? And the cross-coupled transistor pair was offering the equivalent negative resistance. Right. This was some 2 Rp, and you got minus 2 Rp from the cross-coupled negative resistance. Okay. So we'll start with a very interesting circuit configuration in the next class. Thank you.